flat part. If I have a differentiator, it just goes up. There's no flat part to start with. So if you see a picture like this, what does it mean? It means that it is starting with a pole at 0. Okay? It has a term. It will have a term. It will have a term that looks like this. If n is equal to 1, it is an integrator. If n equals to 2, it will also start going down, but at 40 dB per decade. If n equals to 3, it will go down. That means this guy will always start like that. There is no flat here. Understand? Huh? So the slope here will tell you what is the n. If the slope is minus 20 dB per decade, that means capital N is 1. If the slope is minus 40 dB per decade, the slope is 2. Because they are always in multiples of 20. Okay? So this guy tells me it has this guy inside there. The question is, what is capital N? And that's when you draw your straight line. Okay? So you draw your straight line. Okay? So over 1 decade, this is 1 decade here, right? From point 1 to 1 is 1 decade. How much does it go? It goes from 20 to 0. That means capital N must be 1. Because over 1 decade, it went down 20 dB. Alright? So we know now there is a pole that looks like that. That's clue number 1. Now, after a while, you notice that the thing flattens. Now, the only way it can flatten is something is pushing it up, right? What pushes up? Zeros push up. Poles push down, right? Correct? You remember this? Okay. Poles push down, goes down. Zeros go up. So they counteract each other. Right? So that means this guy has been pushed up to become a 0 here. Alright? And I see the blue very nicely. So where should it be? I didn't draw it that nicely. So it's at this point, right? That it starts to flatten up. Agree? It starts to flatten up there. So this must be a corner frequency of a 0 that is going up. So in other words, it must be the corner frequency of something that this is, and then start going up. Right? The loop going down and the going up cancel each other to become horizontal. You understand me? Huh? This guy is going down like that. If there was nothing else, it will keep going down. But it got pushed up to be horizontal here. That means there must have been something that was pushing up here to go up. So that's why you got it like this here. And this characteristic here, alright, this guy here must be a, so the corner frequency is 1, right? S plus 1. Tau is 1. So omega is also 1. Okay? This guy here is a 1 over S. Follow me? I'm doing step by step. So I had a pole, which was an integrator. Then I have a 0 that pushes up to make it horizontal. But at some point later, this guy down again. Right? So that means over here, so this is the first corner frequency.
说话了，正好在那个点上，我忘了不在那个点上。
Right? Okay. So this must have been another pole that goes like that, and then like that. Push it down like that. So this third pole is 1 over tau s plus 1. Tau is 1 over 10 s plus 1. Okay, because the corner frequency is 10. So tau is 1 over omega. Okay. So if I put these three things together, you will find that my GS K times 1 over S times 1 over S plus 1. Sorry. The second guy is S plus 1 times 1 over 10 S plus 1. These are the three parts. Follow me so far? So I'm basically applying all those rules right now to determine what this guy is. And we saw that in the face, both plot, it did not go down. It did not flatten out. So we also know that there is the E delay term there. We've got to find what is the capital L. Yeah? Okay? So how do I find K? We just did it just now. For something that goes straight down, the value of K occurs when omega is equal to 1. If things that have flat like that, then no problem. This guy here is 20 log K. But we don't have this. So we're going to find where inside here, what is that value of K? Alright? Okay, so I look back at my curve here. Alright? And if I look at this curve here, this omega goes to 1, right? You will go up here, it is 0. So 20 log K is 0. At 1, omega is 1, you go up, you hit this curve, it's 20. So this guy here, 20 log K. Okay? So that means K is 1. Huh? 20 log K is 0. So log K is 0. So K must be 1. Alright?
Omega 1
So sorry, at omega 1. No, because you have to use the asymptote. Because just now the analysis was based on the low frequency asymptote. The low frequency asymptote is this red line here. Okay? So this straight line where it crosses 1, that's the value of K. Okay? Based on the low frequency asymptote. Alright? Not the actual value. The actual value is of course the black line here. Based on the low frequency asymptote. Then here, at 1 radian per second, the magnitude of the low frequency asymptote is 20 log K. Alright? Alright, so the last part, so we found K is 1. The last one is L. Right? So now we've got to look at the phase diagram. Now if you look at the phase diagram, over here, okay, what we'll do is we'll just pick one point to figure it out. One point only. Okay? Right? Because we can identify from here. So now we've known everything about the system already. So the system looks like this. Okay? The system looks like this. So GS is equals to S plus 1 over S into 1 over 10 S plus 1 e to the minus SL. This is what it looks like. Alright? So if I look at the phase, okay. Okay, let me change to GJ omega first. Okay, so the phase has 3 parts, this, and that. 4 parts. Right? 1, 2, 3, 4 parts. Okay? There's the 4. This is from that 0. This is from the 0. This is from the first pole. This is from the second pole. Okay? Huh? So if I know a particular value of omega and I know what's the final value, the only unknown is L. And then I can get it from the graph. Okay, so if you look at the graph, the value that has been picked in this example is this value. So if you look at that value, at omega equals to 100, it has minus 370 degrees. Okay, minus 370 degrees. Yeah? So, so I solve for L. Okay? Got it? I solve for L. Okay? Okay? So if you do that, I'm not going to write inside there. We'll switch back here. Right? So this guy here is here. Okay? Then I substitute inside the 0, 1 pole, second pole, and this third part is this. So each of this is calculated up here. This is this, and then 100 feet is here. And then converted to degrees, because it was all in radians. Alright, so I call it TD. So So you put it all together, yeah, you have discovered what GS is. Yeah. So from the graph,
其实它本来是要这个，
okay, on the graph here, at omega equals to 100, it has a phase of minus 370.
它要求这个 TD。
Alright, you can choose anyone you like. Just that this one took that. You don't like my 100, you can choose 10. You don't like 10, you can choose 1. You can choose 55, choose 73. Doesn't matter. Up to you.
什么呢？这时候可以是 omega
Yeah. You don't have to choose 100.
100。
Don't have to.
对，求点
You, the graph is already given to you.
哦，所以你 omega 随便选。
Okay?
对
Huh?
omega 可以选10可以选，但是这 phase
The only thing is that you should choose a higher value of omega because these are all the high frequency. That's why it behave go down. Okay?
choose higher
Another question?
frequency。哦，他看的是这儿。
Yeah.
对，就是下面 higher。 对对。
Because the corner frequency is 10, omega is 10. Tau is 1 over omega.
原来说了。
Okay?
看图的。
Okay? Over here,
这个。
you see, it's 10. That's omega, the corner frequency.
他讲。
Yeah? So tau is 1 over omega. So, that's it. That is all the content that you have. Yep. That's the face. Yeah, this is a polar representation of a complex number. If I gave you a complex number, and this is maths, this has nothing to do with systems, nothing to do with signals. This is complex number mathematics. If I give you a number, AE to the JB, what is the phase? What is the phase of this complex number?
B over A。
Oh dear. B. What is the magnitude of this complex number? Thank you. Yeah. So, what is the phase? Minus omega TD. This is your B. You won't find it in there. You got to go back to your maths textbook. Right? Complex number, polar representation and Cartesian representation. Cartesian is A plus JB. Polar is AE to the JB. Correct? If it's polar, A is the magnitude, B is your phase. If it's Cartesian, magnitude is square root of A squared plus B squared. Phase is arctangent B over A. All this is basic stuff that you learn in secondary school. Right? From where? From here? From here? So this one is what? J 100 I just replaced by J omega what? Omega is 100. This one? What line? Where? Yeah. His phase plus this one is the same one.
No white
Sorry? Yeah. Question. Yeah, because you're looking at phase. Again, complex numbers. Complex numbers are